This is the Intermolecular Forces video. Intermolecular forces are the attractive forces between at least two molecules. They are also generally in covalent molecules. So there are three types of IMFs plus one more. The three types are hydrogen bonding, dipole-dipole, and dispersion. Sometimes dispersion forces are called London dispersion forces. That extra one that we're going to talk about is ion dipole attractive forces. So the first one is dispersion. Dispersion forces are found in all molecules because all molecules have electrons, and electrons can actually fluctuate. They can be unevenly distributed in an atom or a molecule. So if you think of an atom, electrons are generally on the external portion of the atom, still inside the atom, but outside the nucleus, and the protons are inside. When the molecule gets polarized, what happens is the electrons can be found on one side and the protons will be found on the other side of the atom. And the same thing can happen in a molecule. And this type of polarization is the instantaneous or a temporary dipole that can form in all molecules, again because they all have electrons. So if you have two molecules that induce a dipole in one another, you've got a partially positive end and a partially negative end. So that partially positive end will actually get closer to the partially negative end of another molecule, and that is your dispersion force. The second IMF we're going to look at is dipole-dipole. Dipole-dipole IMF is found in polar molecules, and these are the molecules that have a permanent dipole. So for example, if we look at a water molecule, oxygen is partially negative because it's closest to fluorine. Hydrogen is partially positive. So we can have a partially positive end, partially negative end, and we can draw a dipole moment where you have the arrowhead where the negative region is and the positive where the partially positive region is. We can do the same thing with dimethyl ether, where you have the oxygen will be your partially negative end, and then these methyl groups will have the partially positive end. And again, we can draw our dipole moment for the molecule, so it's a permanent dipole. If these two were to be brought together, they would align themselves in a way where the partially negative end, say of the water molecule, will again get closer to the partially positive end of the dimethyl ether, and there will be positive interaction between the two. The third IMF is hydrogen bonding. Hydrogen bonding is also found in polar molecules. Now, this hydrogen bond, do not confuse it with a covalent bond. It is an attractive force between at least two molecules. For a hydrogen bond, a molecule must have fluorine, oxygen, or nitrogen along with their lone pairs. And there must be a hydrogen present that is bonded covalently only to fluorine, oxygen, or nitrogen. Let's look at the fourth IMF, the ion dipole. So this is between an ionic compound and a polar molecule, so you must have them both present to see an ion dipole IMF. For example, we have sodium chloride and water. Sodium is positive, chloride is negative because sodium lost an electron, gave it to chlorine, sodium became sodium ion, chlorine became chloride anion. And we know our water molecule. We know that in a water molecule you'll have a partially positive end where the hydrogens are and a partially negative end where the oxygen is. And so you can see what can happen is that the oxygen molecules are going to orient themselves So they can be very close to that positive sodium ion. And then the hydrogens of the water molecule, which are partially positive ends, they're going to orient themselves so they are closer to the chloride anion. So there's attractive interaction there. We have to consider the strength of those IMFs. Dispersion is the weakest, ion dipole is the strongest. And then after dispersion we have dipole-dipole, then hydrogen bonding, then the ion dipole. What are the consequences of IMF strengths? Well, the stronger the IMF, the higher will be the boiling point, the melting point, the surface tension, viscosity, but the lower will be the vapor pressure. Let's look at some examples of what are the strongest IMFs in each of the following. The first one is methylene chloride. Methylene chloride, if you draw the Lewis structure, it looks like this, where you have your chlorine ends, then your H's, and who is more electronegative? The chlorine ends are. And then where the hydrogens are, that's more partially positive, so we can draw a dipole moment for the molecule. This is permanent, therefore this is a polar molecule, and if the molecule is polar, then it has dipole-dipole forces as its strongest, and of course it has dispersion forces. The next molecule is methylamine. It's a derivative of ammonia. If you think about it, this hydrogen has been replaced with a methyl. And this molecule, if you look at it, we have nitrogen is the most electronegative, and then the rest is actually partially positive. So that's definitely a polar molecule, right? We can draw a dipole moment. So it definitely has dipole-dipole and dispersion, but it has something else. It has the ability to hydrogen bond. So another molecule of methylamine can come in, and we can show that we can have a hydrogen bond between this hydrogen that is bonded covalently to the nitrogen. So that's one of the criteria. And then the other piece is that the nitrogen that is there has the lone pairs that can hydrogen bond. Third example, we have CS2, very similar to CO2. Here we have sulfur is more electronegative than carbon, but there are only two regions around. And so if we look at the dipole moments for each bond, you can see that they cancel each other out. Because of that, it's nonpolar. And because of that, we only have dispersion forces. One more example. Can the following molecules exhibit hydrogen bonding when mixed? So if we go to, oh goodness, if we go to the first example, so we have oxygen plus water. So oxygen is really nonpolar because who's more electronegative, the left oxygen or the right? You cannot tell. But the water molecule is polar. The really cool thing is that the oxygen molecule on oxygen has lone pairs. The hydrogen on water is covalently bound to the oxygen. So there actually can be hydrogen bonding there. And why do we care about this? Well, if you have fish, you know that fish need oxygen to breathe. So oxygen can dissolve in the water, and there can actually be some favorable interaction between the oxygen in the air and the water. The second example is, can there be any hydrogen bonding between ammonia and CH4? We know ammonia is polar. CH4 is nonpolar. Now, CH4 does not have hydrogens coming off oxygen, nitrogen, or fluorine. So no, the two cannot hydrogen bond. The last example is water and formaldehyde. So if we look at water and formaldehyde, so formaldehyde has oxygen. Water has the hydrogen, again, covalently bound to oxygen. So the oxygen from formaldehyde and the hydrogen can hydrogen bond. So hydrogen bond here. So yes, they can. Thanks for watching.